Okay, welcome to this video. In this video we will actually use the equivalent series and parallel resistance formulas, do some computing of equivalent resistances. So the first example that we'll do is the one that's on the screen now. This is what's called a ladder network, and actually has quite a bit of use. It turns out that you can use a ladder network to take a given voltage, and from that get voltage references that you need for an analog to digital converter. And some analog to digital converters are built this way. So our goal here is to find the equivalent resistance of all of these, basically all of these resistors that we have here. Sometimes you'll see this as the written as the equivalent resistance looking into the network. Other times you'll see this discussed as the equivalent resistance between the two terminals of the network. In any case, we want to find the equivalent resistance of this guy. And again, the way we will do this is by finding series and parallel combinations of resistors and combining them into equivalent resistors and going from there. So if we look at this circuit, we want to find either a series or a parallel combination of series or parallel resistors. And if you look at these last two resistors here, those two resistors are in series. How do we know that? Well, again, if you think of yourself as being an electron or some other charge carrier that's moving along, you go through the 1 k ohm resistor here, you turn the corner, and you have to go through the other 1 k ohm resistor. There is no alternate path for the current. Any current that goes through the 1 k ohm, the upper 1 k ohm resistor goes through the lower 1 k ohm resistor. So since these are series resistors, we have then that the equivalent resistance is going to be 1 k ohm plus 1 k ohm, which is 2 k ohms. So what this means now is that from the point of view of everything else in the circuit, which for right now would be everything except these two 1 k ohm resistors that I have circled in orange, I can replace these two 1 k ohm resistors with a single 2 k ohm resistor. So let's do that. Okay, so we have then our single 2 k ohm resistor. Okay, so the next thing I want to do is again find either a series or parallel combination of resistors that I can come up with an equivalent resistor. And the only thing that is there is the combination of these two resistors. You'll notice that they both are connected to that top node and that bottom node. Since they're both connected between the same two nodes, then they're parallel resistors. The equivalent resistance of these parallel resistors would be the product of the resistances divided by the sum of the resistances. And again, if you're not happy working with the prefixes K, M, and so on, you need to get happy with it, so practice it, but you can write this as 2000 times 2000 over 2000 plus 2000. A better way to write this would be 2 times 10 to the third times 2 times 10 to the third divided by 2 times 10 to the third plus 2 times 10 to the third. And so you can plug this expression into a calculator. You can actually work this guy by hand, the one in scientific notation. I'll do that. You get 4 times 10 to the sixth divided by 4 times 10 to the third, which is 10 to the third, which is 1 k ohm. Okay, so with all that computation, what we've shown is that the equivalent resistance of these 2 k ohm resistors in parallel is 1 k ohm. So now to continue the determining of the equivalent resistance of this network, I can replace these 2 parallel resistors with a single 1 k ohm resistor. So let's do that. Chop away all this stuff. And chop away some more stuff here. And so now I can take this guy and replace it by a 1 k ohm resistor. Okay, well, now I want to look for a combination that I can combine again. And it looks like the only thing that I can combine would be this 1 k ohm resistor with the equivalent 1 k ohm resistor I've just computed. And since we've already, a few minutes ago, computed the equivalent resistance of 1 k ohm in series with 1 k ohm, we'll just write down the answer that this is 2 k ohms. Okay, so again, I can combine or eliminate the series combination of these 2 1 k ohm resistors and replace them with a single 2 k ohm resistor. And you can see probably where this is going. If I now look for things that I can combine, again, I find that I have this 2 k ohm resistor and this 2 k ohm resistor in parallel. So without repeating the computations that I just did for 2 k ohm resistors in parallel, I would have the equivalent resistance here of 1 k ohm. So we'll chop off the 2 guys. And replace them by 1 k ohm. Okay, I look again to see what I can combine, and I find again that I have 2 1 k ohm resistors in series. So I have this guy in series with this guy again. Having already worked this particular series combination, I know that that's 2 k ohms. So I will chop away the series combination, replace it with the equivalent 2 k ohms, and now I need to see if I can combine these resistors. I have a 2 k ohm resistor in parallel with another 2 k ohm resistor. So again, it turns out we've worked this one. It's 1 k ohm. We can replace the parallel combination with a single resistor that has a value of 1 k ohm. And we'll even get rid of this ugly brown spot here. So there you have it. That ladder network of resistors has an equivalent resistance of 1 k ohm. You're thinking to yourself, wow, that was a really complicated way to get 1 k ohm resistance. But it turns out that the voltages and currents that you would find inside the ladder network turn out to be useful. And in a subsequent video, we'll probably use the analysis techniques we're developing to find out what those voltages and currents are. So this concludes this video on computing the equivalent resistance of a ladder network.